in Chapter 3, we're going to start talking about how we can use numbers to summarize our numerical data. So before we get started, we're going to be talking about the 3 M's of statistics, which would be the mean, the median, and the mode. So first off, when we're talking about numerical data, we're usually going to be using the mean. We usually only use the mode when we're talking about categorical data. The reason is that when we're talking about numerical data, that's going to be data that can be described as an infinite amount of decimal places, and if that happens, we're probably not very likely to see the mode. So in this section, we are going to be talking about primarily the mean and the median. Now, what the mean is that it's the arithmetic average. When we do this, we usually refer to it as x bar, and this little, it looks kind of like an E almost. What that means is sum. It's a sigma, so you're going to add all of your x values, or all your observations together, and then divide by n, where n is the number of objects in our sample. Okay, so the way I remember the mean is if someone says that you're average, they're being mean to you. The median is if we order the data, and that's going to be the value that sits at the very center. It doesn't matter if you order them from least to greatest, they're still going to be the one in the very, very center. Now, if you have 2 in the center, so you have an even amount of observations, then you're just going to take the average of the middle 2, and that will be your median. The mode is the one that shows up the most often. Again, we're not going to be talking about that one too much, but it's still worth mentioning. Now, for example, let's say we're given the following set of numbers, and we want to find the mean, the median, and the mode. Okay, so if we want to find the mean, which is x bar, what we're going to do is we're going to sum up all of our x values and divide by how many we have. So that would be 1 plus 1 plus 2, and then all these other numbers. So plus ... 7 plus 8 plus 30. And then we're going to divide that sum by how many observations we have. So we have 17. So when we do that, you should end up with 91 divided by 17, which is going to give you about 5.3. When we do the median, that's going to be the one that's directly in the middle. So since we have 17 observations, well, if we take 17 and we divide it by 2 and round it up, so 17 divided by 2, and then this notation means round up. Okay, then what that would be is that would be our 9th observation. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So our median would be 4. And last but not least, our mode is the number that shows up the most often in our observation. So 4 also shows up the most often. So that would be the mode. Now, the next question is which one is probably the best representation of our data? So if we look at our data, first let's analyze the mean. So 5.3, is that a very good representation of our data? Well, numbers like 5.3 would occur around here. Okay? So note that over half of our data is actually below that. Also, I suspect that this number is only so high because we have this weird outlier 30. Okay? Our median is 4 as well as our mode, and I feel like both of those are probably better representations. So I would say best in this case would be the median and mode, and I would really just go with the median because of outlier. Alright, now let's talk about how we can find the mean of our data if we're looking at it graphically. So when we're looking at a histogram, we can think of our histogram as kind of like a seesaw. So what a seesaw is it's an old toy where people used to balance like this and go up and down. So our mean is going to be the fulcrum, or the thing that balances it out. So if we look at this data, it's pretty symmetric. So what that means is that our average is going to be in the center, which will also be where our median is. Now, if we look at this data is very, so which one do you think it is, left or right skewed? This is right skewed. Right, and we know it's right skewed because our center, or our peak, is here and our mean is to the right. So here's a little rule of thumb, is if your data is symmetric, then your mean is going to be pretty close to your median. And then if it's right skewed, well, remember, the x-axis goes in numerical order, so it goes least to greatest. So what that means is that our median is going to be less than our mean. And if it's left skewed, then our median will be greater than our mean. Now let's explore estimating, finding the mean, the median, and the mode using a graph. So if we look at this histogram, first off, what I'm going to do is I'm going to go ahead and label the frequencies. So there's 1, 1, 2, 3, 3, 4, 7, and 5. Okay, so my total amount of observations is 26. Now, if I had to estimate the mean score just looking at this graph, well, I would think that if I put the fulcrum right here, then what would happen is that my graph would tip down on this side, so it wouldn't be balanced. So what we're going to have to do is we're going to have to put the fulcrum, or the mean, slightly to the left, which makes sense because this is a left skewed graph. So I would say that the mean is probably about 40-ish. Now, if I want to estimate the median, that would be the score that's in the center. So if I take 26 and I divide it by 2, that would be about the 13th observation. Now remember, the median is if I put these in order. So since the x-axis is already in order, I can just count up to 13. So I have 1, 2, 3, 4, 5, 6, 7. This would be another 3, so it would be 10, 11, 12, 13, and 14. So my 13th and 14th observation would be in this bar. So that means that my median score is somewhere between 40 to 45. Now the mode is the one that we see the most often. So if there is a mode, I would suspect that it's probably somewhere in this highest peak. So I would say that the mode is somewhere between 45 to 50. Now remember, I'm only estimating these. I don't actually know because I don't have the raw data. But this is a good way to look at a graph and estimate. Alright, so we talked about how to measure a typical value. Now what we're going to do is look at how we can talk about the variation of our data. So how varied is our data? How close is our data to each other and to the average? So doing this, we're going to use something called the standard deviation, and it measures the typical distance an object varies from the mean, or from the average. So if we look at this example, what we can see is that every single histogram has an average at 3.5. So each one has an average at 3.5. Now, even though they all have an average of 3.5, the issue is that they're clearly showing very different information. So what we're going to do is that we're going to look at which one has the most variation. Now, if we look at A, this graph here, what I can see is that around the average, I have a lower frequency than I do at the ends. So what that means is that I have a lot of data that's around 1, so about 250 observations, and a lot of data around 6, but not much around 3.5. That means that most of my data is about 5 whole units apart. Now if we look at C, what I observe is that most of my data, about 350 or more, actually falls around the mean, and I don't have that many falling away from it. So most of my data is only about 1 away from themselves. And for B, it looks pretty uniform. So what I would say is that A has the largest standard deviation, aka the most variation, while C has the smallest standard deviation, or the least variation. That's because most of the observations in C are near each other, whereas in A, they're very far apart. B would have a medium amount of standard deviation if we were going to compare them. So in the next example, we're going to be comparing Alaska, which is Anchorage, Alaska, to Honolulu, Hawaii. Now, both of these areas have an average amount of 12 hours of sunlight per day. However, the amount of daylight that you see throughout the year is very different. So Alaska is very close to the pole, which means that they have very extreme amounts of daylight. So they either have very, very little, or they have a lot of daylight. Whereas in Honolulu, it's very close to the equator, so we're usually not going to have a whole lot of variation. So you might see a 10-hour day, you might see a 14-hour day, but most of them are going to be 12. So when we talk about this, we say that they both have a mean of 12, but the difference is that Alaska has a deviation of 4.5, while Hawaii only has a deviation of 1. So when we're writing this up, what we would say is, for Alaska, a typical day is 12 hours long, give or take 4.5 hours. Another way you could say that is that you could say it's between, so if we subtract 4.5 hours from that, that would be 7.5, and then add 4.5 hours, that would be 16.5. Now when we're talking about Hawaii, we would say the same thing. A typical day is 12 hours long, but now we only give or take 1 hour. So we would say it's between 11 to 13, typically. We actually use this kind of verbiage a lot in our day-to-day lives, and we don't even realize that we're using an average value in standard deviation. So let's say somebody asks you, hey, what's a typical gas price in Washington? Well, it depends what year you're looking at, but you might say, oh, it's about $3.20, give or take 10 cents, right? So it's not unusual to see gas at $3.15, but maybe you wouldn't expect to see gas down to $2.80. All right, so the last thing that we're going to discuss is going to be how to find the standard deviation numerically. So what we're going to be doing first is we have to calculate what the average is. Then after that, we want to see how much each observation deviates from that average. Okay? So we take every observation and we subtract it from the average. Then what we do is that we have to square each deviation. If we don't square them and then we try to add them up, they'll actually add up to 0. After we square them and add them all together, we're going to divide by n minus 1. So how many observations we have? Minus 1. Then we're going to take the square root and we will be done. So for this example, first we're going to have the numbers 6, 7, 5, 8, and 6. So x bar, if we take all these numbers, add them together, and divide by 5, is going to be 6.4. Next, what we're going to do is we are going to find the deviation of every observation from the mean and square it. So we're going to take 6 minus 6.4 and square it. We're going to take 7 minus 6.4 and square it. 5 minus 6.4 and square it. 8 minus 6.4 squared, and 6 minus 6.4 and square it. So we're going to get 0.16, 0.36, 1.96, 2.56, and 0.16. So after we have found all the deviations, which is this step, x minus x bar squared, the next thing we need to do is that we need to add them all together. So when we add all of these numbers together, we are going to get 5.2. So what this step was is that we summed up all the deviations squared. After we have summed up all the deviations squared, the next step is that we need to take all of that and divide it by n minus 1. So we're going to take 5.2 and divide it by how many observations we have, which is 5, minus 1, and then we're going to take the square root. And when we do that, we're going to get about 1.14. Great. We're going to have more videos showing examples of finding standard deviation by hand, as well as finding standard deviation using StatCrunch. For now, we're going to move on to section 3.2.